I'm a principal engineer at AWS. In this session, you're going to learn how to get the best inference performance from AWS Graviton processors using PyTorch. By the way, Graviton processors are based on ARM64 architecture. And to answer the question, like why CPUs for ML? So if you look at the CPU evolution, though originally they were designed for generic workloads like databases and web servers, in the recent generations, CPUs like Graviton have got increasingly high capability for floating point math and vector processing, even with specialized instructions for AI ML inference with, and low precision data formats. So all this together making CPUs a cost-effective option for deploying your ML inference workloads at scale. So to begin with, I would like to share our journey on this project. In fact, we started this project pretty much from scratch, where we had to handle pretty much everything end to end. To begin with, on the optimizations front, we took a handful of models from CV, NLP, and recommender categories and profiled them thoroughly to understand what the operators are, what their runtime requirements are. And once we were clear about the operators, we focused on the GEMM part. So instead of rewriting again GEMM from scratch here, we reused the existing libraries. For example, we profiled OpenBlast, Bliss, ARM Performance Library, and ARM Compute libraries, and found ARM Compute Library, that is ACL, providing the most performant kernels for the platform. That's why we chose ACL for accelerating all the operators in PyTorch for ARM64. So the main challenge with ACL was while the GEMM was performant, the runtime wasn't. So we had multiple performance bottlenecks with the runtime and memory overhead. That is when we had to experiment with pthreads, OpenMP, and multiple scheduling schemes, and tuned all of them for Graviton processors. We also extended optimizations into PyTorch ATen and C10 libraries for the activation functions and memory allocators, and tuned them all again for Graviton processors. So with that, we were able to achieve the targeted performance. And next, our priority was to bring all of those back to the community to enable all the developers. That is where we upstreamed all the features, thanks to the Meta release engineering team, who has greatly supported us during that time. Later, we added all the documentation around user guides and technical guides with the best practices. And also, we brought the release binaries available to the community with all those optimizations enabled by default. Finally, to maintain the features release over release, we added CI/CD infrastructure and also the nightly wheels. So without any delay, let's look at what those features are. Here, starting with the hardware, Graviton processors support both Neon and SVE vector units. Probably most of you are aware that Neon is a vector unit, but that mandates fixed length vectors from the software. When it comes to SVE, it relaxes that requirement. What it means is it provides great flexibility in what can be, in unrolling the loops and how much software can be vectorized with SVE. That's a big deal when it comes to machine learning. And also, SVE supports scatter-gather instructions, which are very efficient for processing the sparse data. And coming to the instructions, Graviton supports both DOT and MMLA for accelerating matrix multiplications in the hardware. And coming to the data formats, along with floating point 32, it supports bfloat16. As many of you are familiar, BF16 supports the same dynamic range as FP32, but with half the memory space. What it means is it can accelerate both compute-bound as well as memory-bound operations, and can deliver up to 2x throughput without any significant drop in the accuracy, which is the right balance for inference especially. And it also supports int8 instructions for supporting quantized operators, which is, again, gaining interest in the generative AI field. Now let's look at what is supported in PyTorch software. This is a block diagram highlighting the components that are optimized for ARM64 in orange. So the main idea to show this diagram is to see how natively the features are integrated into PyTorch, and how PyTorch supports all of them out of the tree. So listing the features, it supports both Neon and SVE GEMM kernels with a fine heuristic in place to pick the right kernel based on the platform architecture, the work size, and the number of threads, and several other factors. It also supports bfloat16 kernels in hybrid GEMM mode. What I mean here is these hybrid kernels accelerate FP32 operators seamlessly without any need for quantization or any post-processing the model or without any changes in the application. It just accelerates and gets you up to 2x better throughput. And of course, the PyTorch also supports int8 quantized kernels for dynamic quantization support. And on the memory front, PyTorch supports primitive caching, which is one of the ways to avoid redundant allocation for the operators, and that cuts down the memory, tensor memory that gets allocated again and again without the caching. And it also supports Linux transparent huge pages. That is another great way to cut down the table walkthrough latencies at runtime and increase the and improve the performance for inference. This feature is mainly very much of interest when it comes to generative AI and also the batched inference, because in both these cases, the tensors are huge and the memory allocations are large, where the Linux THP can be, we can take advantage of Linux THP. Continuing this feature list onto the Torch compile, PyTorch supports Torch compile with inductor backend for ARM64 CPUs, because that is the way you can take advantage of all the ARM compute library, that is ACL kernels, and all the optimizations I just talked about in the previous slide. Apart from that, Torch compile also supports some of the new primitives to give you some of the fused kernels, like the operators which are fused and reduce the runtime overhead. And also it comes with some of the optimized activation functions from the ATen vec library. We are still continuing to optimize Torch compile to add more and more features in the coming releases, and also increase the coverage to more models. While most of these features are automatically enabled on Graviton CPUs, there are few which you can tune at runtime based on your workload. Let me walk you through a sample network and show you how you can tune and improve the performance. Here is my sample network that has simple linear layer followed by ReLU activation, which is typical in any transformer-based architecture. For the weights, I'm using large ones just to mimic pretty much close to a typical LLM model. And for the input, I'm using 256 size here just to show you how the optimizations work at a large batch size. And I'm profiling over 100 iterations just to get a stable run and to show you what the profiler output looks like. So that is the output from the default configuration. As you can see here, AddMM or the GEMM, matmults are the dominant operator in this network, and which is very compute intensive as well. So this is the best case where you can apply your bfloat16 optimization and improve the performance. So you can enable bfloat16 by setting DNNL fastmath mode to BF16. And as you can see here, the latency dropped from 15 to 6 seconds, which is like more than 2x improvement. This is once again large batch and large tensor scenario where you could apply the THP allocations I just talked about. Just by setting THP mem allocator to 1. And here you can see the latency dropped from 6.9 to around 6 seconds, which is around 10% improvement, which is once again great at scale. Next, let me take you to another example. Here I'm using exactly the same network, but with much smaller input size. Here I'm using just a batch of 32. So this is once again the output from the default configuration. If you just do a pip wheel and run this, that is the performance you get. Here it is once again, GEMM is the dominant one. However, it is not very compute intensive. So for this, the recommendation is to switch to open blast kernels, which are like, which come with much lighter runtime and improve the performance significantly. So you can switch to open blast by setting MKLDNN thresholds to be very high so that it falls back to open blast. And as you can see here, the latency is dropped from around 5 to around 2 seconds, which is like more than 2x improvement in this case. So the recommendation is for larger ones, go with bfloat16 and THP allocations. For smaller and single inference scenarios, fall back to open BLAS and make use of its runtime, its lightweight runtimes. In fact, we have simple heuristics in place in PyTorch ATen to pick the right backend, open BLAS versus DNN. However, it is not comprehensive enough to cover all possible combinations. So that is the reason we added this runtime. So recommendation for you is please try both the backends for your workload and pick the one that gives the best performance, because the difference is so huge, almost 2x. So it's highly recommended. We have seen the features and we have seen how to tune them. Now let's look at some real data. For Graviton processors, with all the optimizations we upstreamed in PyTorch 2.x, we were able to achieve up to 3.5x improvements for eager mode. So this was the profiler output for one of the models from Torchbench for ResNet 50. As you can see here, the latencies dropped from 35 milliseconds to 10 milliseconds, so which is more than 3.5x improvement with the optimizations that went into PyTorch 2.x. So the recommendation is, if you are starting on ARM64 and AWS Graviton, start with PyTorch 2. And continuing the performance numbers for Torch compile, here we benchmark close to 75 models, both from Hugging Face examples and PyTorch Torchbench to cover, again, NLP, CV, and recommender categories. Here the improvements are, again, 1.35x to 2x, geo mean of all these different models. So we have, with all these optimizations, Graviton instances are now becoming, cost-effective for CPU-based AI/ML solutions on AWS. All these optimizations are readily available in PyTorch 2.4. And as you know, Graviton instances are available both as Amazon EC2 instances and also fully managed SageMaker service with real-time inference endpoints. So you can go and give them a try. But for you to get started, we already have some resources together here. PyTorch user guide that explains what packages and how to install and all, and tuning guides for the best practices that you can apply for your workload specific. And we have both release wheels and also the nightly wheels for you to easily deploy, and few blogs to talk about the real world scenarios where these are more suitable. Of course, we have come a long way in the last 2 years, but we still have scope for improving the performance further. So here are some of the items which we see at this point. For example, Torch compile optimizations with quantized kernels, or porting FBGEMM features for ARM64, or optimizing embedding bag and copy kernels further, and also on the CI front. So adding more unit tests and keeping them healthy. So these are some of the items I have here, and I'm very much looking forward to collaborate with the community for most of these items. And this is pretty much I have today. Thank you so much.